What if I told you that there was a partial fraction shortcut that they were covering up? No, seriously, it's called the Heaviside Cover-up Trick. Let's go and talk about it.
Let's go ahead and begin with the following example. Here I have the partial fraction decomposition, 3x plus 1 over x times x plus 1 times x minus 1, and here I've went ahead and split up the terms on the right-hand side. And the way that the Heaviside trick works is that you're going to, well, cover things up, as the name implies. So let's go ahead and try to figure out what a is. On the right-hand side, we're going to pretend that everything I've highlighted here in blue doesn't exist. Just the a. We've essentially covered everything up. On the left-hand side, we're going to cover up the factor that corresponds to the thing we're solving for. So here we're solving for a, so we're going to cover up that x. So everything highlighted in blue, we're going to pretend doesn't exist. Now, what we do is that we go ahead and plug in the number that makes that factor 0. So that sounds kind of weird. What do I mean by that? Well, what makes x equal 0? Well, just 0. So we plug in 0 for x. So that'll be 3 times 0 plus 1 over, remember, that doesn't exist. So we're going to have 0 plus 1, 0 minus 1. And this is going to give us 1 over 1 times minus 1, which is negative 1. And this, so that's what we get on this side. And since a is just nothing over here, we have that negative 1 is equal to a. Okay, let's go ahead and try it with b now. So we'll erase that thing. Now we're solving for b, so we're going to highlight in everything except for b. So everything highlighted here in blue doesn't exist. And we're going to cover up the factor corresponding to b. So x plus 1, we're going to pretend that x plus 1 over here doesn't exist. Now we want to plug in the thing that makes that 0. So x plus 1 equals 0 means that x equals negative 1. So we're going to plug in negative 1 for x. And when we do that, we go ahead and get 3 times negative 1 plus 1 over negative 1 times, that doesn't exist, so negative 1 minus 1 here. And that's going to give us negative 3 plus 1 over negative 1 times negative 2. Gives us negative 2 over positive 2. That's going to be negative 1. Once again, it's going to equal b. And then finally, we'll do the same thing for c. So we'll erase everything that doesn't relate to c. So everything except for c gets deleted over here. We cover up the term matching c. And x minus 1 equals 0 means that x equals 1. So we go ahead and plug in 1 this time. And so when we do that, we get 3 times 1 plus 1 over 1. Oops, I seem to have deleted something very important here. Okay, there we go. That fixes it. Sorry about that. Okay, plug in 1 here. Then we got 1 plus 1. That's going to equal 3 plus 1 over 2, 4 over 2, which is 2. That's our c term. And there we go. That gives us all of the, that helps us figure out what a, b, and c are in a very quick way. So, kind of writing down a list of steps here to remember is that the first thing to remember is that you ignore everything except for the thing you're solving for. Ignore the factor corresponding to the thing you're solving for. And 3, plug in the number that makes the ignored factor equal 0. Just 3 steps, and you're basically done with this. Now I should mention something about this, is that you might notice the following thing about this particular problem I've chosen here. The first is that all of these are linear factors, and that all of these are to the first power, and that's on purpose. So the thing to note here is that this trick only works there we go. Sorry, my pen failed to work for a moment there. Only works with linear factors to the first. That might seem like a weakness, but in the next few minutes, I'll talk about how even in the case where you have quadratic factors or repeated linear factors, this is still a helpful trick for making things go by faster. Okay, let's consider another circumstance in which we have some repeated linear factors. So here you'll notice that we have a power of 2 over here. And so far everything is still linear factors. So let's go ahead and try our cover-up trick. Well, first, let's start with C. That seems to be the nice one because it's linear and has everything to the first power. So again, we ignore everything except for C on this side, and we ignore the factor corresponding to C. And the thing that makes this one is -1, so we plug in -1. So 2 times -1 plus 1 for -1 minus 2 squared is going to give us -2 plus 1 over -3 squared. That's -1 over 9 is equal to C. Great, we have that one. But now we have a problem here where we have this square term to worry about, which I mentioned before could be a problem. And the thing you want to do here is that you only want to apply this trick to the thing with the highest power. What do I mean by that? So when you try to do our Heaviside Cover-up Trick, it's only going to tell you what A is. It's not going to tell you what B is. Here, if you try to solve for B with the cover-up trick, you'll get that B equals 5/3, and this actually turns out to be wrong. And so you can get wrong answers if you use this thing for lower powers. So the thing to remember here is that you can only use the trick for the highest exponent. So corresponding to that factor. So everything's fine for C because that's already to the first power, and there's no other high powers. For A, the highest one's 2, so we only figure out what A is. So let's go ahead and do that. So cover-up trick, we ignore everything except for A. We cover up the factor corresponding to A. And we go ahead and plug in the numbers. Let's see, the thing that makes this thing 0 is 2. So 2 times 2 plus 1 over 2 plus 1 is going to be 5/3 equals A. Cool. So we got 2 of the terms figured out, which is a huge time saver. So even though this trick doesn't tell us what B is, we still have 2 of the terms figured out really quickly, and we can use those to find B. So let's go ahead and do that real quick. To figure the rest of this out, we just go ahead and solve the usual way. So the way we do that is by clearing the denominators. So multiply everything by the denominators we have over here, and we'll get that 2x plus 1 is going to equal A times x plus 1 plus B times x minus 2 x plus 1 plus C times x minus 2 squared. And then to make my life easier, I'm just going to go ahead and expand this out real quick. So that's going to be x squared minus 4x plus 4. Okay? So, and the beauty of this is that we already know what a and c are, so we can go ahead and replace them with what they are. So 2x plus 1 is going to equal 5/3 times x plus 1. We don't know what b is, so we'll leave that alone. And we know that c is minus 1/9. And then we'll go ahead and just mindlessly distribute things. Go on algebra autopilot, if you will. Plus b times x squared minus x. And so it's going to give us bx squared minus bx minus 2b, or not to be, that is the question, minus 1/9 x squared plus 4/9 x minus 4/9. Okay, cool. And now the interesting thing to note here is that there's actually kind of two ways we can solve for b here. The thing is, we have a polynomial on this side, and we have a polynomial on this side, and so if they're equal, their terms should match. And so there's two ways you can do this. And so that means if they match, that means every single one of their terms should match. So all of the constant terms on this side should add up to 1, because that's the constant term over here. All the degree 1 terms should add up to 2, because that's what we have over here. So our degree 1 terms here are 5/3 x, negative bx, negative 4/9 x. So we get that 5/3 plus 4/9 minus b equals 2. That's one way you can see it. Am I missing anything? I think that's all of them. Let's see. You could also, that's one way you could see it. Another way you could see it is that our constant terms are 1, 2b, and 4/9. So you could also have 1 minus 2b minus 4/9 equals 1. Or there's a third way here, because there's kind of like a sort of pretend 0x squared here. So you could also see this as our square terms are these two, so b minus 1/9 equals 0. Why do I give you all these? The point is to show you that you have options. And those options are, here are 3 different ways you can figure out what b is. You just got to solve these equations for b. And in any case, you'll get that b equals 1/9. The other thing is you want to pick nice ones. This equation down here is the easiest by far, so why not choose that? But just knowing 2 of the factors made our lives a whole lot easier in trying to solve this partial fraction decomposition. So even though we can't use the trick the entire way, it does make things a lot better. Now let's go ahead and look at a case where there are quadratic factors. So let's go ahead and consider the case with quadratic factors. Well, here it's the same with repeated linear factors, in the sense that it's only going to work for the ones that have this or something like this. But even having that makes our lives a whole lot easier. So let's go ahead and try this example here. Well, we go ahead and do our cover-up trick, so we ignore everything except for c and the factor corresponding to it. And here we're going to plug in 1. So we do that, we get 1 over 1 squared plus 4 is equal to 1/5, and that's going to be our c term. So great, we have one of the 3 figured out. What about a and b? Well, here we're going to have to solve it the usual way. So we get that x is going to equal ax plus b times x minus 1 plus c times x squared plus 4. Well, harkening back to what we just did a moment ago, we already know what c is, so we can go and solve for that. Ax plus b times x minus 1 plus 1/5 times x squared plus 4. And so now we go ahead and expand things out and figure out what our polynomials should be. So x, multiplying things around here, is going to go ahead and give us ax squared minus ax plus bx minus b plus 1/5 x squared plus 4. Okay, let's go and take notes here. The first thing to observe is that we have no x squared term over here. So it's like a 0x squared is in there, basically. And so if we collect all of our x squared terms here, they should add to 0 because of the equality here. So these are all of our x squared terms. So we know that a plus 1/5, wow, that's a 5, believe it or not, plus 1/5 should equal 0, which means that a has to be negative 1/5. Well, that was easy. Well, what next? One thing we can do is we can go ahead and, am I missing a term here? I am missing something here. That should be 4/5. Sorry about that. Okay, great. And we have some options for b. The first is that we can look at linear things here. So here, there's a 1 there. So when we get all of our linear things together, we have just a and b. So negative a plus b should equal 1. We know that a is negative 1/5. So that means that b has to be, wait, sorry, if it's negative 1/5, that should be positive then. One of these days I'll remember how to do arithmetic. Okay, in that case, that means that b has to be 4/5. Another way that you can do that, because the beauty of this method is that you have options, is to see that there's no constant term over here. So it's like there's a plus 0 over here. So all of our constant terms should add to 0. Our only constant terms are b and 4/5. So negative b plus 4/5 should equal 0, which again gives us that b is going to equal 4/5. So hey, that was pretty quick. We quickly found this term. So again, even though this method doesn't give us all the factors right away, it still is very helpful in finding all of them. Now it's kind of worth an investigation to see, why does this trick even work in the first place? So that way you can rest assured knowing that you're not actually practicing dark sorcery. Let's take a moment to explore why this trick works in the first place, and also why it doesn't work in the case of repeated factors or quadratic factors. So let's look at the first example that we did. Well, how does this work? So the first thing that we're doing is, let's go ahead and try solving for a again, is that we're effectively multiplying by the factor that corresponds to the thing we're solving for. So for solving for a, I want to go ahead and multiply both sides by x. So there's an x here, you get an x, you get an x, everybody gets an x, whether they like it or not. And now the next thing we did, and so that's kind of why you can pretend that this factor isn't there here. It's going to cancel out. Now the next thing we did is that we went ahead and plugged in the thing that made that 0. But you might notice is that you can't really technically plug in the thing that makes it 0, because then over here on this part of the equation, you get 0 over 0, which is indeterminate. So the way we get around that is by taking limits. Well, when we take the limit as x approaches 0 in this case, well, you're going to get, and since limits are additive, you can do each of these individually. Over here we have no problem. If you take limits x approaches 0, you're just going to get 0 here and here. So that's why we can effectively ignore those. So why can we ignore the x over here? Well, it's because the limit as x approaches 0 of ax over x is just a. So that's why we can just only consider the a, because as we approach the value that we're plugging in, it's the only term that matters. And the same justification with the other factors would explain why you're able to cover up things except for b, or cover up things just for c. It all just comes down to limits. So knowing that, let's go ahead and see what goes wrong in the repeated factor case. In the repeated factor case, well, we already know that everything's going to work out just fine for c. We just did that in the example above. Everything's cool when we have single linear factors. Well, next we can try multiplying by x minus 2, because let's try to solve for b. Well, when we do that, that's only going to cancel out one of them over here. It's not going to cancel out both of them. The other thing that goes wrong over here, and so that's an issue. The other thing that goes wrong is that on this side, you'll end up getting ax minus 2 over x minus 2 squared. And if you try to take the limit as x approaches 2 here, try to do that, this thing does not exist. And so math kind of breaks when you try to solve for b. Okay, so why does it work for a? Why can we still at least do the highest power? Well, because then we kind of fix the problem. In that case, if we just multiply by x minus 2 over here, then that gets rid of both of those. Okay, everything's so far so good. You get x minus 2 squared over here, minus 2. And you once again take the limit as x approaches 2 in each case. In this case, you'll get the limit equals 0, so that goes away. In this case, you also get the limit approaches 0, so you're good here. Okay, everything's canceled out here, and then here you'll get the limit approaches a, so you can cancel those out, and you're only left with a. So everything works out okay as long as you're solving for the highest exponent. Lowest exponents creates the issue where the limit doesn't exist, or you're dividing by 0. So, and now let's look what goes wrong in the quadratic case. Well, the problem with the quadratic case is that we're trying to plug in the thing that makes this 0. And if you have an irreducible quadratic, by definition, it just can't equal 0. X squared plus 4 equals 0 has no real solutions, which means that we can't hit 0, which means things don't disappear. Like if we want to make c go away, if you have x squared plus 4 over this thing, since this top part, since x squared plus 4 can never equal 0, this thing, no matter what limit you take, has no hope of hitting 0. So you can't make the c disappear like you could in the previous case. So that's just not going to work.
Well, that concludes everything for today's video. Thank you for tuning in, and let me know what you think in the comments. If you have any suggestions for future videos, go ahead and let me know. And share this with a friend who you think might find this useful or interesting. Don't forget to like and subscribe, and I will see you in the next video.